Let's talk about multidimensional Black-Scholes equation, or, well, that we're going to use to price what we call basket options, or basically options that depend on more than one type of stock, more than one type of asset. So we're trying to value, so here's what I'm asking you to consider. We're trying to value an option that depends on N stocks, stock 1, stock 2, stock 3, all the way up to stock N, and time. Regular Black-Scholes only depends on one stock and time. So just as an example, this is an option I just made up, but I mean, anything you can think of, we can price with this formula. So say you own an option, and what it allows you to do, it gives you the right, not the obligation, it's an option. You can buy shares in stock 1 for 10 bucks. So it's like a call option. But at the same time, if you exercise the option, you get to buy shares in stock 1 for 10 bucks, and you have to sell shares in S2 for 20 bucks. So it's like a call and a put sort of combined together. You have to do both things or not do anything. And you're only allowed to do this if some third stock is below $30. So this option depends on 3 stocks. What's its value? What's its payoff? Let's look at some scenarios then. So the first thing I get to do is, so I have to do both of these at the same time. I don't get to just buy the stock 1 and not sell the stock 2. So here's like possible prices for stock 1, stock 2, stock 3. Say that at expiry, at the payoff, it's $12, $21, and $20 respectively. So because stock 3 is less than $30, I'm allowed to decide if I want to buy stock 1 for 10 bucks, sell stock 2 for 20 bucks. Do I want to buy stock 1 for 10 bucks? Yeah, it's worth 12 bucks. So if I do that, that's like a $2 profit. But I also have to sell stock 2 for $20, and it's worth 21, so that's like a loss of $1. But do I want to do this? Yeah, in the end, I'll make $2 here, I'll lose $2 here. It's a payoff of $1. So in this scenario, at this payoff, I'd go, yes, let's do it, and I make $1. What if stock 1 is all the way up to 20 bucks? So buy it for 10, yeah. Stock 2 is at 15. Sell it for 20? Yeah. That'd be a payoff of 15, but I can't because stock 3 is above $30. So I'm not allowed to do it. So in that case, the payoff to me is actually 0 because I can't do it. Other scenarios, well, okay, the buy, as long as the stock 1 is above 10 bucks, I would want to buy. Here, don't want to buy. Do I want to sell it for 20 bucks? Yes. I can't even do it anyway, and even if I did do it, I'd make $1 here, lose $2 here. In the end, my payoff would be minus. So the payoffs are a minimum of 0 if we don't exercise it. So I can't even do it because stock 3 is above $30, and even if I could do it, I don't want to because I would lose $1 doing it. Here then, well, okay, here stock 3 is below the $30, so I can if I want to. Do I want to? Well, I don't want to buy stock 1 for $10, exercise this kind of call part of the option, because I'd be losing $2. Do I want to sell stock 2 for $20? No, I'd be losing $3. So I can do it, but if I did do it, I would lose $5, so I'm not going to do it. So far, the only scenario is the first one where I'm allowed to do it and I would make money, so I would choose to do it. Last case, stock 3 is below the $30, so I'm allowed to do it. Okay, do I want to do it? I could buy stock 1 for $10. Okay, I could buy it in the regular market for $7, so that's worth like -3 to me. But here, stock 2 is worth $9, and I can sell it for $20, so that's worth $11, negative 3 in the 11, a payoff of 8. So I would do it here. I'd lose money on one thing but make more money on the other, so yes, I would do it. So all these possible scenarios, and that's only with 3 stocks. Stock 3 is kind of like, S3 is like a switch. Am I allowed to do it or am I not allowed to do it? Stocks 1 and 2 are sort of part of a call like and put like option linked together. I have to do them at the same time. How do I price this? Well, first let's make the multidimensional Black-Scholes equation. Oh, but maybe we could think about like where is it I'm allowed to even do this? So I'm going to think of stock 1's value as the x coordinate, stock 2 value as the y coordinate, stock 3 value as the z coordinate, and then here's a picture of where I would actually do this. So I want to be on the purple side. So red is above red, don't do it. Below, so below 30, the z is 30. Below 30, I'm allowed to do it. This line is on the purple side. In this region, I would make money. On the red side, I would not make money. So below this z equals 30, on the purple side here, I'm allowed to do it, but I would only want to do it on this side of the purple line, of the purple curve. How do I make that purple curve? Well, let's go back and look at our scenarios here. If I exercise it, what's my profit for the buy? It's a call, and so a call, that's going to be, normally that would be S minus the exercise, so that's the stock, or X. That would be the X value minus 10 bucks. That's the call if I exercise it. Plus, let's look at this put value, which would normally be E minus the stock, so that's 20 minus the Y value. So this is equal to my profit here. Not profit. This would be my payoff if I exercise it, which would just be the plane X minus Y plus 10. That's what this curve is here. It's a plane, X minus Y plus 10. And I set it equal to 0. That would be on the plane. On the purple side is when it's greater than 0, so my payoff would be positive. So I would exercise it if I could. So what you're seeing here is in this region here is the region where I'm allowed to and I would want to. All right. So I'm going to get rid of that because that's just the payoff for drawing the curve. So now let's look. That was an example, kind of a complicated example, but we'll have to make our Black-Scholes that prices this thing. Each asset. Now I'm going back to the multidimensional, so I'm going to have n stocks. Each stock, I'm assuming, follows log normal with its own drift, mu sub I, and its own volatility, sigma sub I. So each stock is moving with its own equation, with its own stochastic differential equation, its own log normal equation. So they have different sigma i's and different mu i's. We're trying to value this option that's dependent on all the s's and time. Now last time when we made our regular one-dimensional Black-Scholes, we differentiated, we took dv, and that was equal to the first, all the first order partials, so v sub s and v sub t, ds and dt, and only one second order partial, v sub ss, because all the other second order partials would have powers of dt that were bigger than 1, and we called that too small and got rid of them. We could also see that if we left them in, as we made dt go to 0, that they disappeared on their own anyway. But so just following the sort of general heuristic way we were doing it last time. Anything bigger than dt to the power of 1 is too small and we can get rid of it. Then what did we do here? Well, we had just ds, there was no subscript I. We subbed it in here, we subbed it in here. We made our portfolio that was the value minus delta times the stock and figured out what delta. We're going to do the same idea here. But now let's take the multidimensional equivalent of this. So first I need all the first order partials. Well, now V is a function of n s's. So I need the V sub s1, ds1, V sub s2, ds2, all the way up to plus dot dot dot, all the way to V sub sn, dsn. That's all of the stock first order derivatives. That would be like this piece from before. And then I need the V sub t, the derivative with respect to time. Well, there's only one time, so that's only one piece here. So now I've got all of the first order derivatives, partial derivatives taken into account. Now we need all of the second order partial derivatives. And just like we only need the stock ones, except now I could take the derivative with respect to stock 1 and then stock 1, or stock 1 and then stock 2, or stock 2 and then stock 1, or any combination. So this plus dot dot dot, this is like all the pairs differentiate with respect to some stock, let's say the I stock, and then differentiate with respect to the J stock. And they could be the same. I and J could be the same. All right, there's a lot going on here, but let's try and make our formula a little bit more concise. I took this as the only thing that's changing is it's 1, 1, 2, 2. So this becomes the sum of all the first order partials. The derivative of V with respect to S sub I times D sub S sub I. That's that sum. There's only one time derivative, so there it is. We need all the pairs of stock with stock I and stock J. So I'm summing over I goes from 1 to N, J goes from 1 to N, and this is all of the V sub S sub I and S sub J with D sub I, ds sub I and ds sub J. That's all of this pieces here, dot dot dot. There's all pairs. So where does this half come from? Oh, the half is the same half here. It's the Taylor polynomial half, right? 2 factorial. It's still there. So now I've got my dv here. Now everything I understand except for this ds sub I and ds sub j. In the one-dimensional case that was already done, ds squared, we ended up squaring this piece. When we squared that piece, we got some dt squared, too small, power of dt bigger than 1. We got some dt's and dx's, that was like dt to the power of 1.5, too small, got rid of. And we got some sigma squared s squared dx squareds. And dx squared, quadratic variation, turned into dt, and we kept that. So in the one-dimensional case, we replaced this ds with our sigma squared s squared dt. But so I understand, like, if I and j are the same, I understand that. D sub si and d sub si, I get that. That's going to be sigma I squared si squared dt. But what about if they're not the same? What's that? Okay, well, let's take a look. If we multiply these two pieces, remember each one has its own drift and its own volatility. I'm going to get some dt squareds here for first and first. dt squared, too small, going to drop it. Some dx I and dt, too small, going to drop it. Some dx sub j and dt, too small, going to drop it. The only thing that has a chance of surviving is this, when the dx sub I and the dx sub j, what's that? This sigma I, sigma j, si, sj, that's working out just like it was in the one-dimensional case. It's just that this highlighted piece here that I got to worry about. So these d sub, each one of these d sub xi's are, it's a random variable, and the expected value is 0. So we can say the expected value of that random variable is 0. They're drawn from a normal distribution, and its variance is 1. So then this is just the product of these two. If it was dx sub I and dx sub I, then that would be the correlation of dx sub I and dx sub I. They're the same. That correlation would be 1. But if they're different, like they are here, we can replace this with the correlation of those two random variables. Now, if I and j are the same, the correlation of two random variables that are the same is 1, and that collapses down. We've preserved this, one-dimensional thing that we have. But we've got these two random variables whose expected values are 0, and then the product of them would be just the we're talking about the expected value of the product of them, would be then their correlation. So now I understand what this piece is going to be. So we have our my bad, dt, right? Scaled quadratic variation, the same idea. Its variance is scale. So dt, quadratic variation. So now, right, because when we put this one in for ds, we got sigma squared s squared dt. For the dx squared was the dt. Here it's correlation dt. All right, so now I've got this dv with the dt's in the right spot. The only randomness is in here. The rest is going to be just like when we did it in the one-dimensional case. Just so we have it in our notes, let's put that then, the expected value of this product. That's that sigma dt here. Okay, now I've got my dv. We're going to set up, the rest of this is going to follow like we did in the one-dimensional case. We're going to set up our portfolio. Which is going to be buy one of these options and short, oh, wait a minute, there's like n stocks. Yeah, I got to short a little bit of stock 1, a little bit of stock 2, a little bit of stock 3. So I'm going to short the sum, my delta, that's a little bit of each stock. Delta is still the amount of stock I that I short. And I runs from 1 to n. So there's the portfolio that we're going to set up. All right. Change in the portfolio. This will look super familiar, right? Change in the portfolio is going to equal to dV. Now, deltas are numbers. So there's our change in the portfolio. And for this dV, let's put in what we have it to be. And this looks super familiar because it's the exact same setup as we did before. Whoop, don't want to do that. Okay, so now I've got the change in the portfolio is equal to this piece here. Where's the randomness? There's randomness still in the ds sub I because there's still some, well, where's the randomness? There's the randomness in each ds sub I. There's randomness here and there's randomness here. You know where we're going with this. We set the delta s, we set the deltas, and now there's n of them, equal to the derivatives and then this piece will cancel this piece. So now the change in the portfolio is equal to, so now we got to pick the deltas, we picked them that way. So now the only thing that's left is this, and it's all dt. There's no randomness. It's all deterministic. That means that this should grow at the risk-free rate. It should be as if I took the change in my portfolio should be as if I took pi dollars at the risk-free rate of return for dt amount of time. We're like almost there. Now dt, 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 I can cancel the dt off all three parts. And I mean, pi is just, pi was minus this delta s sub I. I'm just replacing for what pi is, r. Oh, but what's delta? Delta was, we set delta equal to this v sub s sub I, the partial derivatives. Okay, we're like right there. That's the multidimensional Black-Scholes. Let's clean it up a little bit by multiplying this r through just to make it look more familiar. And the most familiar, let's bring this over to the other side, make it a plus here. There. This is the multidimensional Black-Scholes. If there's only one stock, this turns into regular Black-Scholes. Okay, before we jump into this, because I mean, I gotta solve this, or at least write down the solution. We do have the solution to this in one dimensions, right? It was that integral from 0 to infinity, discounted piece, e to the, we had that, and we did a lot of work turning it into the heat equation, and then using our solution to the heat equation, then putting it back. That was about an hour to solve that. But we'll have a multidimensional solution to this. But before we jump into that, let's just see what's here. When we say solve this equation, what do we mean? Because it's a multidimensional partial differential equation. Well, we're trying to find the v whose partial derivatives fit in here. Now, what do we need to measure? R is the risk-free rate of return. That's 28-day T-bill rate, you can say. The S sub I, the value of the stocks, that we can just get in the market. The sigmas, those are the volatilities. We have ways of measuring that. The most sort of the quickest way, the sort of quick and easy way, is to take the annualized standard deviation of the returns. These correlations, though, okay, we gotta get those values. We gotta worry about what the correlations are in the returns. So how to get those correlation values? We gotta talk about that. But they're all those are okay. I'm gonna lie to you for a second. I'm about to say sigma, that's a constant. Rho, that's a constant. R, that's a constant. The lie is that they're not all constants. We even knew that if we measured the volatility differently by taking a slightly different data set, right? Like take a data set of like a month, but start on Wednesday versus start on Tuesday, we'll get different sigmas. It's even worse for correlations. So they're very buzzy, fuzzy numbers. But this math assumes that is treating them like they're a number that we can measure. So we'll do that. What's next then? We got to write down the solution for this. So we're solving this multidimensional Black-Scholes equation. And I'm just going to straight give you the solution. Here it is here. The process would be similar to, except like way more complicated than how we'd solved it in the past. But there's some pieces here. So this is the solution to this partial differential equation with this payoff. So we're integrating over the y's here, right? The y1, y2, y3, 1y for each stock. We integrate over them, so that sums out. Now, what are the pieces? Well, we've got this correlation matrix, this sigma matrix. And it's a symmetric, it's positive definite, but for us it's symmetric, right? That's the important thing right now. With one, so this is how dxi is correlated to dxj. So the stocks are correlated to themselves, so that's why there's ones down the diagonal. There's correlation between stock 1 and stock 2, stock 1 and stock 3, all the way up to 1 and n. And this would be correlation between stock n and 1, but that's the same thing as 1 and n, so that's why it's symmetric. So we got our correlation matrix. Now, that shows up in here, the determinant of the correlation matrix, t minus t, that's the tau, that's the time left. This is our discount, because we're summing up this integration is summing up over all the possible. Then we're discounting that. This 2 pi square, almost like the square root of 2 pi, but it's n, how many stocks there are, 2 pi t minus t. That's the that's like the multidimensional Gaussian, 3D bell curve kind of thing. I guess ND. We've also got this alpha vector, and the alpha vector is made up of the ith component. There's one component for every stock. This looks like similar to those D formulas that we had before, but these are each one of the components. So this, when I integrate with the specific payoff, then is this solution to this multidimensional Black-Scholes with the specific payoff at the end. Now, my last question here. What happens if n is equal to 1? In other words, there's only one stalk. Well, if there's only one stalk, then this equation collapses down into regular Black-Scholes. What is the answer collapse down to? Now, it should collapse down into a regular solution of Black-Scholes. Yes. But if there's only one stalk, then the correlation matrix is just a matrix with 1 in it. So the determinant is 1. So let's just take this piece here. Let's take this solution and just think about what happens if there's only one stalk. Well, then the correlation matrix is just the matrix with 1, so its determinant is 1. Square root of 1 is 1, so that disappears. There's only one sigma, sigma 1. N is 1, so this is just the square root. So I'm going to write that as square root then, instead of to the power of 1 over 2, because I think that's not what I want. I think that makes it more familiar. And I'm only integrating once. The payoff is only with respect to that y1. There's only one y1 here. Okay, so far that, that simplifies like we think it would. Let's look at this alpha. This is with alpha being a one-dimensional vector because there's only one stalk. That's 1. That's 1. That's 1. That's 1. Now, the correlation matrix was just that with one stalk was just 1, so its inverse is just 1. So then this is a one-dimensional vector, so one-dimensional vector transpose is the same thing. So this whole top piece, the correlation matrix is just a 1 in the middle, its inverse is just a 1, so this whole expression just ends up being like alpha squared. So I can get rid of it. And there's only this alpha 1, so let's just pop it in here. Zip. Okay, there's the answer. This looks super familiar. It does collapse down into, and we knew it would, collapse down into the solution to the one-dimensional Black-Scholes equation.